Well, welcome guys. What we're going to look at today is an experiment to investigate Hooke's law and how springs behave. So I'm going to talk you through what we have to do experimentally, because this is something you might need to know for an exam question. We're going to do the experiment and then we're going to draw a graph and analyse the data that we've got. So I hope you know that Hooke's law is all about how does force affect the extension of a spring. And we're going to reduce the word force to capital F, and the extension, we're going to use the letter E for extension. It used to be X when I was at school, X for extension, but it's going to be E in the equations that you deal with. Okay, so this is what we're trying to investigate. Yep. How does force affect how a spring will extend? So we're going to set up a little experiment. So if you were asked to describe what you would do, I might suggest that this is what you would do in the laboratory with me. So here's the desk, surface of the desk, and you'd set up a stand to hold a spring. So I'm just going to draw the stand like this. Here we go, there's your stand. And you'd put a spring on that stand. So here's the spring, and our spring sort of key ring on there, and then you draw them like that. Okay. And then the bottom sort of keyring bit of the spring allows you to hang slotted masses on it to change the force. So you might remember that our slotted masses have a sort of hanger. And then you can put masses on 1 Newton, 2 Newton, 3 Newton, etc. of force. So 10 of them would be a kilogram, wouldn't it? 10 newtons per kilogram. So each one is 1/10 of a kilogram. So each one has a weight, a force downwards of 1 Newton. But that's no good. We'll just find that a spring gets longer. We need to find out how it affects the extension of the spring. So what we need to add to this is some method of measuring the extension. So what I tend to do is I tend to put a little pointer on the spring, like that. Okay, it has a special name, a fiducial pointer, but a little pointer. And I'm going to sit here a ruler. Okay, the ruler is going to be vertical, and when I take those masses off, the top of the ruler will be lined up with the zero, or at least the little arrow here will be lined up with the 0 on the ruler. So here's my ruler. More correctly, it's a rule, but never mind. There we go. And that's going to be calibrated in centimetres. So that's going to be the extension in centimetres. And I'll just remind you, I hope you can see why this pointer is down here now, because we've got some weight pulling downwards. But if we were to take those off, this pointer will be level with the top of the ruler. Okay, and I'll just mark our force here in newtons. I'll do it that way. Okay, I could have put that in brackets. So let's have a look at a few things here. Firstly, it's quite difficult to get the ruler close to the spring, so I've used a pointer. Okay. Secondly, this pointer arrow needs to be really close to the ruler. So, something like that. Okay. So you can see very clearly where it's pointing to on the ruler. If it's too far away, there'll be a lot of error. And as you move your eye up and down, you'll find that the position of this appears to move down and up. You get something called a parallax error. So, what are we doing here? We're making sure that the pointer is really up against the scale. It can actually be over it slightly. We'll get our ruler the right way up. Okay, that's got to be the 0 at the top. And do you remember we're not going to have a 0 error. We're going to make sure that when there's no masses on here, there's no force downwards, that the pointer is on the 0 of the ruler. So loads of experimental detail there. Finally, a little bit of health and safety. Okay, so I'll put that in red because that's the scary thing. Health and safety. Okay, I'm not going to detail it here in massive detail, but if you remember, health and safety is what's the problem? Okay, yeah. What could happen? And then how are you going to fix that problem? So the problem is something like the heavy weights are so heavy, and this is on the edge of the desk, the whole thing's going to fall off. So maybe the problem will lead to you getting injured by a stand falling onto your feet. So what's the fix? You're going to clamp the stand to the desk. Okay. If you were using large masses and you put your hands underneath here and something went wrong, okay, what's the problem? Rapidly falling masses. Yeah, what could it do? It could damage your fingers. What's the fix? Don't put your fingers underneath the weights. Okay, so I always say, what's the problem? Yeah. What would happen? And therefore, what's the fix for that? Okay, so I'm not going to write a long list of these, but common ones for the exams are clamp the stand. Okay, put some foam rubber here so if the masses fall, they don't go crashing down and hit the desk and bounce off. And one they're always really keen on is what if the spring came off here and it would go flying across the room and it could catch you in the eye. Okay, so spring comes loose. What happens? It goes flying and hits you in the eye and gives you a serious eye injury. What's the fix? Goggles. Okay, so I'll leave you to think about those. Interestingly enough, the way I'm going to set it up, I'm going to make sure I set it up so there's absolutely no risk whatsoever of the spring coming off the stand and going flying, as it were. So let's head off into the laboratory now and take some measurements. And the measurements we need to take, yeah, are the force and the extension. So as we put different weights on here, 1 Newton, 2 Newtons, 3 Newtons, what extension do we get? So I'm going to draw a little table. I've got it on a big sheet of paper to show you, but my little table over here, little sketch, is going to be the force that I put on the spring in newtons, and I'll do the extension in centimetres. It really should be in metres, but that will do. Okay, so let's go over to the apparatus and get some data. Right, so I've set up the apparatus here in a similar way to the way you would if you'd come into school today. And I've got my stand, I've got the ruler, and I'm going to make sure the ruler is vertical. Okay, I've got my little spring up here and the pointer on the spring, and it's lined up with 0 on the ruler. I've got some slotted masses over here, and so what I'm going to do is put those weights on, and I've got myself my table of data where I'm going to put the force and what the extension is in centimetres. Now, force is going to be 0 to begin with, so I shall write down that there's no force on it, 0, and the extension is 0. Okay, and then what I'll do is get 1 Newton, okay, 1/10 of a kilogram. I'll hang that on here carefully. It's a bit difficult to do from this angle. Okay, let's get my pointer on the right side of the ruler. There we go. Okay, now we're up and running. And then it's more for your side of the experiment, but what I can do here is look at where the pointer is pointing, where it's lined up on the ruler, about 2.4 centimetres. Okay, so I'm going to write on my table that I've got 1 Newton and I've got 2 6.4 centimetres. Now, you'll see this whole table in a second, but I've been very careful not to write the units in the table. You just put numbers in the table. So what I've got to do next, go to 2 newtons. Here we go. And I'll come round your side, have a quick look. Okay, so I've got about 6.5 centimetres. So 6.5 for 2 newtons. That's interesting. I'll just quickly do 3 newtons. And then you've got the idea. Okay, so for 3 newtons, about 10.5 centimetres. So I'm writing those numbers in my table, and I'm going to continue putting slotted masses on, but I think you're all aware that I want to stop when I've maybe put 7 or so newtons on, because if I put on more than that, I might stretch the spring a bit too far. I might go past its elastic limit, and if I do that, it's no longer behaving like a proper spring. It's actually been permanently damaged. It's been permanently deformed. So I'll get my table of data here, and I'll continue to make a few more measurements, and then I'll take a screenshot of that, and we'll go back to the board and we'll analyse our results. So let's have a look at what you got. So we got our table of data, yep. And what I want you to do now, in a minute I'll get you to pause the video, is to get a sheet of paper, graph paper if you've got it, but if not, line paper will do. As best you can, draw a large set of axes, okay. Make the y-axis force in newtons and the x-axis extension in centimetres. So do you notice your table looks a bit back to front? Force, for this experiment, we're going to have going up this axis, okay, not across. Let's not worry about why that is. It just makes it easier to understand. Okay, mark on evenly going up, so maybe 1, 2, 3, 4, 5, 6, 7, maybe 2, 4, 6, 8, 10, etc. Okay, as best you can. And then plot your points as accurately as you can with little pluses. Okay, and then do you remember you draw the line of best fit. Now, this is a straight line. Okay, I don't know if you've got any anomalies. I don't think we'll have an anomaly, but if we had a funny point here, we'd draw a circle around it and say it's an anomaly, and we completely ignore it. But the line of best fit's quite interesting. You might find that it doesn't quite go through 0, 0. It should do. Okay, sometimes it goes just above 0, 0. So there's a line of best fit. Okay. Now this is a little bit unusual. For GCSE, your line will always go, I think, through 0, 0. Let me just tell you what's going on here. Our springs were actually pulled together slightly, okay, out of the box. So you actually needed a force, a little bit of force, just to get the coils to begin to separate. They were actually in compression already. Okay, but what we're going to do is we're going to assume that that's not the case, and we're just going to draw the line of best fit through 0, 0. So I've explained this little problem here if you get it, but what we'll do is I'll do all the teaching of this with the graph going through 0, 0. Okay, so pause the video now. I'm going to put the data up on the screen in a second. Go away. Draw your graph, and then we're going to come back and analyse the shape of the graph and what it tells us about the way springs behave. So I hope your graph looks something like this. Probably hasn't got an anomaly. Well, I know it hasn't got an anomaly because I did the experiment well. And we've put the line of best fit through 0, 0, okay, which makes the understanding a little bit easier. by the way, this is quite difficult to understand. If the line was over here and it had an extension for no newtons, that's rubbish. That can't be the case. And what happens, it's a very difficult exam question. If the line went up in the same way but had an extension for nothing on it, what the student's done there is they've put the ruler at the top of the spring and they've got a length before they even got started, before they put the weights on. What they've measured is the original length of the spring, okay? And then all the other readings will be the original length of the spring plus the extension, okay? Not a good way to do the experiment. Always start by measuring the extension, not the whole length of the spring plus how much it goes down by. So I've made this one a little bit easier. So I've got one other little mathematical thing I'd like you to do, okay? I'd like you to work out the gradient of this line, okay? The gradient. I don't know if you remember how to work out gradients. But the gradient is always equal to how much you go up by divided by how much you've gone across. The change in y over change in x. Some maths teachers say the rise over the run, if I do it that way, yeah? The change in y divided by the change in x. Physicists have got a really clever way of doing it. Change in, that little symbol there means change in y divided by change in x, okay? Rise over run. So could you go to your graph now and make this a big triangle? You know, draw a line somewhere to make it a big triangle and divide how much you've gone up by, okay, by how much you've gone across. The number will be less than 1. It'll be quite a small number, okay? But what you're doing is finding the gradient of this line, which is the same at every place. It's a constant gradient, okay? And we'll talk about what that number means in a minute. So pause the video now and go off and work out your gradient. So I hope you got a value for your gradient. I'll show you what I got. When I did it, I divided the rise by the run, or the change in y over change in x. And my gradient, should be pretty similar to yours, came out at 0.25, okay? And this has got units, hasn't it? It's got units. You divided force by extension, okay? You divided force, newtons, by extension, centimetres, okay? So the steepness of our graph is measured in how many newtons we would need to get a centimetre extension on our spring. The number of newtons needed for a centimetre. And if that's a small number, we don't need many newtons to stretch the spring. If it's a large number, we need lots of newtons to stretch the spring out, okay? So a small number will mean the spring is not very stiff, and a large number will mean that you'll need a lot of newtons to get a centimetre stretch. It'll be a very, very stiff spring, something like a car suspension spring. So I hope you got a number a bit like that for your gradient, and we're going to look at that next. So we're bringing all of this together now. We found that when we increase the force on a spring, the extension increases. We expected that, of course, and we found that it's a straight line. So force is directly proportional to extension. In other words, there's a positive correlation here, okay? And as the extension goes up by a certain amount, so we say 5 times, the force needs to be 5 times bigger. That makes sense. If we make the spring 10 times longer, we'll need 10 times the force. Okay, so it's important that if you describe this graph, you'll say it's a positive correlation, and you'll say that force is proportional to extension. In other words, there's always a physicist lazy way of writing this. Force is proportional to extension. I nearly wrote X there, didn't I? Okay, because of my old-fashioned teaching. So force is proportional. Now that sort of fish sign, or it looks a bit like an alpha in Greek. Okay, that is the symbol we use for proportional. Now that can only be true if the line is a straight line. It's a good one to learn for exams because it explains straight line graphs really well. Okay, so what we're going to do next is go, okay, how can we turn this into an equation? And the hint is this gradient, which doesn't change. It's a constant. So let's bring everything together now. We know we can describe this relationship as force is proportional to extension. But we want to make that an equation. So we want to say F equals something times by extension, a constant, something that doesn't change. Just fit it in there. Okay? So, what is constant? What doesn't change? Well, the gradient of the graph doesn't change, so the gradient must be the constant. Now, for annoying reasons, constant with a K, constant, you'd think it'd be a C. So F equals K, the constant, times the extension. And that constant is the gradient of the graph. It doesn't change, it's constant. And do you remember I said that this number tells you how stiff a spring is? So this is the spring or Hookean stiffness. Okay? And that equation is the one you will have to use at GCSE if they ask you what's the force, stiffness minus multiplied by extension, or what's the extension, force divided by spring stiffness. So what we'll do finally is we'll look at what has all this got to do with Hooke's law. So I said, what has all this got to do with Hooke's law? Well, what Hooke said was that if you put a force on an object and it extends, yeah, sure, okay, it stretches, but the extension is proportional. In other words, if you draw a graph of force against extension, so if you double the force, you get double the extension, triple the force, triple the extension. If that's true, okay, then my equation here holds, it works. The spring is Hookean, okay? But if this graph starts to bend or wiggle, then it's no longer got this constant in it, okay? It's not Hookean. And of course, I think most of you are aware that if we could keep using this formula, okay, so we say that 1 Newton gives 1 centimetre, 2 gives 2 centimetres, 3 gives 3, a million newtons gives a million newtons can't give a million centimetres. We will have broken the spring. So this graph doesn't go on forever. There's a point where it'll begin to curve and then the spring will break. And the very moment it begins to curve, none of this is true. It's not proportional. It's not obeying Hooke's law. Okay, we've gone past the elastic limit. And they often ask you to draw that in exams. And if you go past the elastic limit, you have permanently deformed or permanently damaged that spring. So I hope you have a really good understanding now of Hooke's law and how it applies to springs. But most importantly, you remember or you can learn what is the experiment you do to see what the relationship is between force and extension for something that is Hookean, a spring. And if you wanted to investigate something that was not Hookean, like an elastic band, doesn't produce a straight line, okay, then you would just replace the red spring here with an elastic band and see what graph you got. And it would be a different graph. Just to end, okay, in case they ask, but what's the graph like for when you start to take the weights off. Okay? Well, if you've not damaged the spring, not gone past its elastic limit, then as you take the weights off, the extension will get shorter and shorter and shorter and shorter, and with no weights, there'll be no extension because you haven't damaged the spring. So when you load it, you go up the line, and when you remove weights, you go down the same line. All of the stuff that Hooke said applies as long as it's a spring and you haven't gone past the elastic limit. So I hope you enjoyed that video and found it useful, and you now feel you're an expert on springs. You can always go back and look at a few bits, but remember, we've looked at the mathematics of how springs behave, but we've also looked at an experiment to see what the force extension characteristics are of a spring. Anyway, it's a shame you can't do that in the laboratory with me, but no doubt you'll be back sometime and we'll do some more experiments then. And I look forward to seeing you when you're back.